So good afternoon in Taiwan and good morning in Prague. Today is our great pleasure to have Professor Jean-Philippe Lessard from McGill University to give a talk. He will share his research on computer-assisted proof on existence of many complex invariant sets, including PI solutions. And today he will focus on the Navier-Stokes equation, which is very popular in Taiwan and also maybe all over the world. So we are all very curious about his research. Let's welcome him.
Thank you very much. Jia Huang, I don't know how to say your name, but yeah, thank you very much.
Just call me Jia, yes.
Jia, thank you very much, Jia, and thank you very much for this opportunity to speak in your webinar on nonlinear evolutionary dynamics. It's a great pleasure to be here. Of course, I would prefer to be in person in Taiwan. Maybe one day I will go there for the first time. So yeah, so today what I will do is that I will give hopefully a general overview of these computer-assisted proofs methods in the world of dynamical systems, especially PDEs. I will present an example which is about the Navier-Stokes equation, but hopefully I will kind of present a more general approach which could be applied to different types of equations, including delay differential equations, ODEs, discrete dynamical systems, and infinite dimensions. And the purpose really is to compute some interesting objects. Okay, but as I said, this talk is about the Navier-Stokes equation. So I'm going to first, recall a little bit background on Navier-Stokes. So as many of you know, these are equations for fluids, to model fluids. And in that case, what we have systems of equations. So here the unknown is the velocity of a fluid. So in that case, x here could be in R3, it could be in R2. Let's say we focus mainly on three-dimensional domains. So you can really think of x as being three-dimensional, and the velocity depends on each point in R3, and it depends on time. Here P is the pressure, and rho is kind of it's scaled by the density of the fluid. Nu here, which is a very important parameter, is the kinematic viscosity, and F is the external forcing term. And that's going to play a big role in this talk. I just have a question. Do you see if I move my mouse, do you see it?
Yes.
Okay. All right. And then yeah, they were introduced by Navier and Stokes a long time ago. I mean, in fact, it's exactly 200 years ago that Navier proposed these equations. So that's kind of these are old, but they're still very used nowadays. And in fact, there's a lot of important questions about their solutions. And one of them is the famous Millennium Prize problem, which is about long-term existence of solutions. So basically, given an initial velocity and an initial pressure, is it the case or not that the solution exists for all time, right? So in other words, are there any blow-ups? So if you think of simple ODEs, right, you could have an initial condition, and then you want to know if the solution exists for all time. For some ODEs, very simple ones like U prime equals U square, for instance, the solution, the answer is no. The solution will blow up. It will explode in finite time, so it will not be defined for all T positive. So the same question holds now for the Navier-Stokes equation in 3D. If you take a three-dimensional domain, and it is not known yet. Some people believe there is a blow-up. Some people believe there's no blow-up. So that's still pretty much an open question. And of course, there's a lot of research and efforts worldwide to try to understand and to try to answer that by the affirmative or the negative. But from the viewpoint of dynamical system, let's say this may not be the most interesting question. In fact, going back all the way to the philosophy of Poincaré, I mean, for him, it really is the matter of understanding bounded solutions, okay? So if you have, say, a dynamical system, then what are the kind of asymptotic solutions which exist for all time and which are bounded? So regardless of the fact that some initial conditions could lead to a blow-up, I mean, there's a lot of initial conditions which could lead to global existence, or could lead to kind of the notion of compact invariant sets, right? So The philosophy of Poincaré is really the one that we are adopting in my field, say, because we're interested in trying to understand really compact invariant sets. And compact invariant sets, they have very specific features. They are often very smooth because they are existing for all time. So if you, again, you think of a simple compact invariant set that could be a steady state, or that could be an equilibrium solution or a time periodic solution. So these objects, they live for all time, and because of that, they persist. Say the smoothing in the equations, they inherit a lot of nice smoothness properties, and often they're very low dimensional. So low dimensional in the sense that if you look at this cartoon here, then what we have fixed points, we have connecting orbits, we have periodic orbits, and that could be the phase portrait of a PDE, for instance, where each point here represents a function. So if you look, say, for that limit cycle is really a one-dimensional object in an infinite dimensional phase space. So that's what I mean by low dimensionality. And the fact that these compact invariant sets enjoy smoothness and the fact that they're low dimensional means that numerically we'll be able to compute them, exploit the smoothness, and exploit the fact that they're low dimensional. And what we will do is that we'll reframe or to recast these objects as zeros of nonlinear maps in some infinite dimensional Banach spaces. I will come back to this later. Okay, but our philosophy basically to study Navier-Stokes is that instead of really trying to understand initial value problems and see if solutions exist for all time, what we will do instead of that, we will say, well, we're going to focus on specific type of bounded solutions, steady states, periodic orbit, connecting orbit, and we will try to see how these can eventually organize the long-term dynamics, and then see if we can kind of understand global dynamics of Navier-Stokes by studying specific type of objects. Okay, so I'm talking about steady states and about periodic orbits. So let me review slightly the kind of knowledge that we have right now about the dynamics in Navier-Stokes. And if we want to do this, then we have to go back to the work of Seren in 59. And he published two seminal papers on the existence of solutions in the limit of large viscosity. If you think of Navier-Stokes, it's a model for fluids, right? And then there is this number, this parameter nu, which is the kinematic viscosity. So if nu is really large, then you can think of being like in a honey, or if nu is extremely small, then you could think of being in the air, right? Where the viscosity is really small. But in the limit of the large viscosity, when you are, like, let's say, in a very thick fluid, which doesn't necessarily want to move so easily, like honey, for instance, then what he did was to prove existence of globally stable equilibrium solutions. And he also showed the existence of periodic solutions on a three-dimensional bounded domain subject to time, periodic, boundary data, and body forces. Very important to realize that he proved the existence of periodic solutions, but then there was some time periodic boundary data or body forces. So you can think of this as an external forcing term, which is periodic, and that forces the existence of a periodic solution. Okay, in the limit of the large viscosity. And after that very important work, so a lot of people started to study periodically forced Navier-Stokes. So again, it's studied Navier-Stokes, but if you go back to the equations of motions here, then we have this external forcing term. So you can think of the external forcing term here as being time periodic. And again, it's as if, say, you have a fluid and you exert some sort of periodic forcing. So it's very natural to think that the response to that periodic forcing, which will be time periodic, will actually lead to the existence of a time periodic motion in the fluid itself. Okay, so that's kind of the setup in which Seren and then other people studied Navier-Stokes. So for instance, in 1967, Caniel and Shinbrock proved the existence of periodic strong solutions for small time periodic forcing. Again, important to realize it's time periodic forcing. Takeshita in 69 proved existence of periodic solutions for any time periodic forcing, and that was for 2D domains. And afterward, lots of people started to study, prove existence of periodic orbits for non-autonomous Navier-Stokes. And by non-autonomous, I mean when you have an external forcing term, which depends on time, then from the viewpoint of dynamical system, that leads to what we call a non-autonomous system, because there are terms that are depending explicitly on time, equations of motions.
And here, sorry to interrupt, here you see Xia in the end, HSIA.
Yes. I see. So that's that. I see. That's your.
He's a professor in National Taiwan University, my supervisor. Yes.
Sure. Very good. Okay, thank you. All right. So it's fair to say that our understanding of periodic flows in response to time periodic forcing is rather advanced. Okay, and it has been understood for a very long time. But the same cannot be said for what we call spontaneous periodic motions. And by spontaneous, I mean periodic motions or periodic flows which are driven by a time-independent forcing. So again, think of Navier-Stokes, and now think of Navier-Stokes with an external forcing term, but now which does not depend on time. Okay, so it's not like you have a fluid which is stirred periodically and then there is a consequence of periodic motion which arises as that. No, now it really is Navier-Stokes with a time-independent forcing term. And an example of that would be the famous experiment of von Karman, where you have a cylinder immersed in a fluid, and then you have a steady flow coming from the left, and then you'll have this periodic motion that will arise. And if you had very large viscosity, in that case, that periodic motion would not be present. But for small enough viscosity, then there is this phenomenon here which is happening, and then that leads to the existence of a periodic motion, which is, again, not a consequence of the external forcing term being periodic, but it's more the advection, which is the nonlinearity of Navier-Stokes, which is creating that. Okay, so that's an example. I will not study the specific model here in this talk, but it will be, in some sense, a similar idea. And okay, so what we want to do is that we want to develop an approach to prove existence of spontaneous periodic orbits in Navier-Stokes for time-independent forcing term. Yeah, I'm putting computer-assisted here, so I mean, I guess I will soon jump in the world of computer-assisted proofs, but what is important to realize is that we are not doing computer-assisted proofs for no reason, right? We are doing it because there are very few techniques to prove existence of these kind of motions using standard analytic tools. And why is it? Well, because the Navier-Stokes equations are nonlinear and they're infinite dimensional. That's a pretty serious obstacles, right? I mean, if you think of systems of equations in finite dimensions, if you have, let's say, a set of nonlinear equations that you want to solve, I mean, it's extremely hard to actually prove the existence of solutions, right? So you can use Newton's method, you can use iterative methods to compute approximate solutions, but even to prove their existence, it's a non-trivial task. So now imagine that you moved in infinite dimensions, and then you are in infinite dimensional function spaces, then that's even harder, right? So how do we, as mathematicians, face these kind of questions? How do we study these nonlinear equations? I mean, they could be finite dimensional or they could be infinite dimensional. Now I am going to step out a little bit of Navier-Stokes, and I'm just going to ask these very general questions, right? So how do we do that? I mean, there's quite a lot of mathematics that has been developed over the last hundreds of years to try to understand and to develop machineries to study nonlinear equations. And I would say that there, in a cartoonish kind of world, there are two main towers of mathematics that have been developed to understand these nonlinear equations. And I would say that the first one would be the pen and paper analysis tower, right? So on the left, what you see here is that you see absolutely beautiful mathematical machineries which were developed over the centuries to study nonlinear equations. If you think of nonlinear analysis, topology, I mean, topology was developed by Poincaré himself somehow to understand periodic motions in celestial mechanics, right? So the world of algebraic topology is a consequence somehow of Poincaré's struggle to get his hands on trying to compute exactly periodic motions. Same thing with Floer homology. If you think of Floer homology, it's a very fancy tool in abstract mathematics. But if you think of the origin of Floer homology, it was developed by Floer himself prove Arnold's conjecture, which was about to prove, to study existence of periodic motions in Hamiltonian dynamics. So again, I mean, these tools were developed to try to understand, characterize solutions of nonlinear equations. I mean, bifurcation theory, Le-Richarder degree, symplectic geometry, calculus of variation. So there's a lot of beautiful mathematical tools that were developed over the years to understand nonlinear equations. I would say that would be like the pen and paper analysis tower. And on the right, you have the tower of computers, or computational world, I would say computations, which since the advent of the digital computer, I mean, that world has exploded, right? So you name it, there's so many beautiful tools from the world of computations that have been used to understand solutions of nonlinear equations. I'm going to use a lot of these tools today. In fact, I will use tools from both worlds. And, scientific computing, Galerkin approximations, I'm going to do that today, continuation methods, the fast Fourier transform, which we also will use, interval arithmetics to actually control floating points error, scientific computing, and so on. So these two worlds have been developed, I would say somehow not quite separately, but I have a feeling way too often that pure mathematicians on the left and applied mathematicians sometimes on the right are like fighting against one another, and then they see these towers as separate. And I always didn't like this kind of dichotomy. And in fact, the world of computer-assisted proof really is trying to build a bridge, because we really use both worlds to actually prove theorems, right? So we really use the fact that we can compute with the tools from the right, and then after that we use the computations in more theoretical sense, and we try to prove existence of true solutions close to approximation, using the pen and paper analysis world. And more details to come. Okay, so basically that's the kind of where I stand in this world of how to study nonlinear equations. Is that why not combine both the strength of both worlds? Okay. So I'll be more explicit about computer-assisted proofs, but let me just say, our goal is to develop now computational approach to prove existence of periodic motion. So there's a lot of different ways to use the computer to prove things, and the specific way I will use the computer, we are using the computer to study these nonlinear equations, is as follows. So we want to compute an algorithm, to construct an algorithm that will provide an approximate solution to a problem. We compute, we obtain an approximate solution, and then after that, we want that very close to that approximate solution, there exists a true solution, or an exact solution, and we want explicit bounds within which the true solution is guaranteed to exist in a mathematically rigorous sense. Okay, so that's going to be using fixed point theorem, and in order to get these, to prove that there is a fixed point, we'll use contraction mapping, and then to use contraction mapping, we'll have to build bounds, which will depend on the numerical approximation, which will depend on the function space that we choose, and so on. So I will describe that in details for Navier-Stokes. Okay, but in general, that's basically our view for how we treat computer-assisted proofs. Okay, and well, I mentioned before that this field draw inspiration from different fields, and you can see some here, and early pioneer works of what I'm presenting today, it really goes back all the way to the work of César in 64, and then Lanford in 1982. He used similar ideas to prove existence of the Feigenbaum conjectures, which is about universality of the Feigenbaum conjectures and Feigenbaum constants in pair doubling bifurcation. So he used the computer to prove the existence of a fixed point. In that case, he used Taylor series expansions to represent the fixed point. But again, these ideas that I will present today, they go back quite a while in the past already. Mishakov and Mrozek in 1995 proved the existence of chaos in the Lorentz equation using the computer and using topological methods like the Conley index theory. And a famous more recent result is the one of Tucker in 1999, who solved one of Smail's problem about the existence of the Lorentz attractor in the Lorentz equation. Used normal form theory and the rigorous integration of the flow of the three-dimensional Lorentz equations, and so on. So these are early pioneering work. So I just wanted to mention that, what I talk about today is really coming from already a rather long tradition of computer-assisted proofs in dynamics. Okay, so what I will do now is that I want to present a global overview or general overview of what we use in general to prove existence of zeros of nonlinear maps. Okay, so I will spend maybe the next 10 to 15 minutes explaining the general ideas of the approach that will be completely independent of Navier-Stokes, of the periodic motions in Navier-Stokes. I will present the global idea, and then after that, I'm going to apply that general approach to Navier-Stokes. Okay. All right. So now I mentioned that I was going to talk about something very general. So let's say I have now a nonlinear map, f of x equals 0, and x could represent a lot of different things. Okay. So I am interested in dynamical systems. So for me, I've been studying over the last 20 years, maybe I've been studying solutions to ODEs, to delay differential equations, so periodic motions, equilibrium solution, invariant manifold, and so on. So X could represent a lot of different things. And of course, we use the computer, so we use some tools from approximation theory. So for instance, in our context today, X will be representing a periodic orbit. The way that we will represent the periodic orbit will be to extend or expand solution using Fourier coefficients. So X will represent all the Fourier coefficients of the periodic motion. Okay, and in fact, for the problem of today, we will not know a priori what the period of the periodic orbit is. So we'll also have to include the period as an unknown. So in that context, the unknown X will contain infinitely many Fourier coefficients, and it will contain the period at the same time. Okay, but that will be the application that I will have for this problem. But let's say we apply this strategy to a lot of different type of problems. All right, so now we have a problem of the form f of x equals 0 to solve in a Banach space. So it's going to be in general, it's going to be an infinite dimensional nonlinear map. Okay, so the difficulty is that problem could have a lot of solutions. It could have infinitely many solutions. There could be a unique solution, but in general, it's nonlinear, infinite dimensional. So there could be a lot of solutions, right? So often it's impossible to actually compute them exactly, to obtain them exactly. So what we propose here is that instead of trying to really get exact solutions or exact closed form formulas, so what we propose is slightly different ideas to actually construct small little balls centered at numerical approximation, in which it is proven, and again proven in a rigorous mathematical way, that true solutions exist in these small little balls. Okay, here I made the balls quite big to portray the so that you could see, but hopefully the radius of the ball will be so small that we will not even be able to see that these are balls. Okay, so this is what we propose. So how do we get these small little isolating balls? Okay, so what we have is that we have an infinite dimensional map. So again, for Navier-Stokes, what we will have is that we will have infinitely many equations to solve and infinitely many Fourier coefficients. So what we'll do, we'll take a finite dimensional reduction to that problem. Okay, we will consider, say, a finite dimensional reduction of dimension, say, capital N. Then we will apply numerical approximation scheme, so Newton's method or continuation or iterative methods, homotopy methods, whatsoever. There's a lot of different tools from scientific computing to compute approximations of zeros of finite dimensional maps. So that will be the first step, right? And I will denote by x bar a numerical approximation of f of x equals 0 in a Banach space. Okay. Again, all of that will be done by using a finite dimensional reduction. And then after that, we use the computer, and I will be very explicit about this in the context of Navier-Stokes. We construct an approximate inverse for the Fréchet derivative of the map at the approximate solution. For the approximate solution, I'm using a little bit I'm using slightly notation here. So even though if it's a numerical approximation, I can still embed it in my dimensional space and think of that as an element of my infinite dimensional Banach space. So basically this here really is true Fréchet derivative at x bar. What I want is I want to construct a linear operator which acts as an approximate inverse. And then I verify that A is injective. Why? Because then I want to study the fixed points of a Newton-like operator about the numerical approximation. And if I have the injectivity of A, that means that fixed points of T are in one-to-one correspondence with the zeros of F because of the injectivity of A. Now, basically, what I want to do next is I want to show that so on a closed ball of radius r, which I do not know a priori, I want to show that T is actually a contraction mapping. I want to find a radius such that the ball of radius r, centered at the numerical approximation, is under the map T, is mapped into itself, and T is a contraction on that ball. And the tools that we are going to use to actually verify that this is in fact the case, that T is a contraction mapping on that ball, is using what we call the radial polynomial approach. But this is nothing else than the Kantorovich type theorem, and that's the theorem. Okay, so that's kind of a very general theorem. The proof is rather easy to do, and the statement goes as follows. So we have a Newton-like operator, which is given by x, T of x equals x minus a times f of x. We assume that T is C1, and then that r to be positive, r will be the radius of the ball centered at the numerical approximation, and you consider two bounds. Okay, the first one is epsilon, and it is essentially measuring how good a numerical approximation you have. So you take x bar, you apply it under T, and then you look the distance from x bar, from the numerical solution. And because of the construction of the Newton-like operator, this is equal to a times f of x bar. And now you take the norm in your Banach space. And then once you have this, then you define an epsilon, which is going to be an upper bound for this. Okay, so at this point, we're going to have to use the representation of the map that we have. We're going to have to use the fact that we have a norm in X. We have to do some computations, and we will use what we call interval arithmetic to control all possible errors at that point. And then epsilon will be a rigorous number for which we know that, say, T of x bar minus x bar, the norm in X, is less or equal than epsilon. That's the first bound. Second one is to compute the Fréchet derivative, the operator norm of the Fréchet derivative of the Newton-like operator on the ball of radius r centered at the numerical approximation. So by definition of T, once again, this is nothing else than the operator norm of I minus a times the Fréchet derivative of df. And this, we say that it is less or equal than kappa of r. So again, this kappa of r, this constant depending on r, will have to be done explicitly, right? So that's going to be a combination of functional analysis, operator theory, nonlinear analysis. We'll use Banach algebras there to compute these constants. I will not go too much into details, but the idea is that to compute this constant or this polynomial, say in R, or this function of R, then that's really where the left tower, like the pen and paper analysis tower, will play a role. Okay. So if you think of A, so now if you think of A as being an extremely good approximate inverse for df, right? And if you take R to be very small, then that's almost going to be zero as an operator, right? So if you think of R as being really small, then this Fréchet derivative is almost at x bar. And if A is the exact or would be a very good approximate inverse, then this is going to be this product will be almost the identity. And there's very good hope that this is very small. And this is very important because here's the theorem. So if P of R is less than 0, then T is a contraction with Lipschitz constant kappa of R, which is less than 1. So in some sense, if you take a very good approximate inverse, then the kappa of R will be really small, almost equal to 0, and there's very good hope that there will be a positive R for which this is negative. Okay, so that's basically this one inequality to be satisfied here. If it's satisfied, then T is a contraction. Then you can show that T maps the ball into itself, and the contractions, the Lipschitz constant kappa of R is less than 1, and therefore T has a unique fixed point in the ball, and by injectivity, F has a unique 0 in the ball. So that's that's our theorem here. And this quantity is often called the radii polynomial because it's kind of encapsulating all the bounds from what we need. Yeah, it's putting all the bounds in one inequality. And you can see that, for instance, you cannot take the R too small, because think of this here as if you take R to be equal to 0, well, then epsilon is not negative because epsilon is an upper bound for the defect, basically. So you can see that you cannot take the R too small, because in that case, the polynomial will not be negative. And if you take R too large, in that case, well, in some sense, when you think of kappa of R here, then that's an upper bound for the Fréchet derivative. So if you take it really large, it's going to grow, right? At some point, it will become larger and larger. And in some sense, it makes sense that you cannot take it too large, because the philosophy here of this approach is that we're using a Newton-like operator, and Newton's method is going to be a contraction only close to a true solution, right? So if you get really far from it, then it's not going to be a contraction anymore. Why? It's because Newton's method is based on the idea that locally the linear terms are winning over the nonlinear terms. So if you get too far from the true solution, then at some point the nonlinear terms are going to start kicking in, right? And then you will not have any more contraction of Newton. So you can see that you cannot take R too large either. So there's this sweet spot here, and this is what this polynomial kind of encapsulates. That can be seen also from the fact that if you have x bar numerical solution and you take the radius to be too small, which is here, for instance, then you will not recover a ball which contains the true solution, right? Which is here portrayed by x hat. So you have to take it in a, you have to take it carefully. All right, but the idea is then the following. So you have a map, and then you actually take a finite dimensional projection, you compute an approximate solution, and then you get this approximate inverse A, you compute these bounds, and then you hope that you'll be able to find a positive R so that it's negative, so that this polynomial is negative, in which case you'll have a unique zero of F in the ball of radius R. Okay, so that's the general idea. So now I want to...
Hello, can I ask a question?
Yes, sure.
Do you assume that the Fréchet derivative of F is invertible or surjective somehow? Because if the F is tangent to the solution, then this Newton method is a little bit problematic, right?
Right. I mean, of course, we need... So in that context, there is an if, right? There's if here. So if this is satisfied, then you can show that because kappa of R is less than 1, you can show that this in fact leads to the fact that df is going to be invertible by construction of our operator A.
And what kind of sufficient condition for df can guarantee this P of R is negative for some R? Like finite rank approximation, compact, or surjective?
So I mean, F is usually not compact. So F itself is often going from a space to a space to another space, right? So just F itself, as you will see, I mean, F usually we go from a space of regular function to a space of quite less regular function. The thing is that A here, the way we choose A brings back the regularity that we lost. So so F itself is actually an unbounded. It's not even mapping a space to itself. And the same thing with df. But df inverse brings back regularity. But in the context of this Newton-like operator, that really is the A here, which has to be chosen in a way that A times F maps the space into itself. But to go back to your question, of course, if we are at a bifurcation, then this method does not apply immediately, but you can change the F and you can change the setup so that you can interpret a bifurcation point as, say, a zero of a map, which is going to be a slightly more complicated map, for which this approach will apply as well.
Okay, thank you.
But in this context, what we need, of course, here it's going to work for hyperbolic points. So for points which are isolated, right, which are not, I mean, for which the norm of the inverse or the inverse exists, and then the norm of the inverse is not so large.
Okay, thank you.
Yeah, but we have several papers in which we actually study bifurcation points using that approach, but the F has to be changed, right? But that's possible. Okay, so what I want to do now is that I want to move to the Navier-Stokes equations, and then I'm going to apply this general strategy to prove existence of spontaneous periodic orbits in the Navier-Stokes equations, and that's joint work with Jan Bauer van den Berg from Amsterdam, Maxime Breden from École Polytechnique in Paris, and Leonard van Veen from Ontario Tech. Okay, so going back to Navier-Stokes, so in fact, what we started doing when we were working on this, I don't know, maybe 6 years ago, then we started to work with the original version of Navier-Stokes, and we started to do numerics, we started to do our machinery that we already had developed for say 10 years on different problems. And the fact that in the Navier-Stokes equation we had a pressure, and then there is also incompressible equation, and that led us to a problem with the part of having to compute an approximate inverse, because we didn't have a nice structure which we could exploit in the setup of the original velocity version of Navier-Stokes. And what we realized is that the engineers are often not working directly with Stokes, but they're in fact applying the curl to Navier-Stokes, and they're moving to the so-called vorticity formulation of Navier-Stokes. And we decided to actually do that. And in that case, when you apply the vorticity, so when you apply the curl to Navier-Stokes, the nice property of that, so if actually go back to all the way to motions, so if you apply the curl to this, then the nice thing is that the actual pressure will disappear. And because of the pressure disappearing, so you have more of like you have kind of get rid of that unknown, which you can recover afterward. But the nice part is that you apply the curl to it, and then you ignore the fact for now that you need to have incomprehensibility. But in fact, this is also something that we will impose in our function space. Okay, but basically the idea is that instead of working directly with Navier-Stokes, then we apply the curl to Navier-Stokes, the pressure drops, and now we have a setup which is going to be a setup with less unknowns, namely that we'll just have to solve for the vorticity. And afterward, we can recover the velocity. I will show a result. Okay, so after applying the curl or the curl to the velocity, then we obtain the vorticity, and F omega here is going to be the curl of the external forcing term. And now the linear part, they don't change, so it's really the partial of omega, the vorticity with respect to t minus nu kinematic viscosity times the Laplacian, plus some nonlinear terms. The nonlinear terms become a little bit more complicated because I had an advection term in Navier-Stokes, but now I applied the curl to it. So there's a couple of terms there. I'm not going to put them explicitly, but yeah, I could provide some expression. Okay, so what we do now? So what we do is that now we are looking for space-time periodic motions, because what I didn't tell you is that what we're doing in this work is to study solutions on the 3 torus. The 3 torus is a choice, right? But if you go back to actually even the Millennium Prize problem, the setup from the Clay Foundation that Pfefferman wrote, Charles Pfefferman, then the global existence is also, there is one open problem on the 3 torus. So people are interested in on this, in these domains, even from the point of view of theoretical viewpoint. Of course, some real life problems are not on the 3 torus all the time, but this is our setup here. Okay, so this is a disclaimer. Our method works for periodic motions on the 3 torus for the moment. Okay, so since we are on the 3 torus in space, then solutions are periodic in the 3 spatial directions, and we are looking for a time periodic function. So therefore, it's the vorticity that we're looking for is periodic in 4D, so in 3 spatial dimensions and 1 time dimension. And so that's why we can expand in Fourier expansion. We can in Fourier series the vorticity, and now we have e to the I n tilde dot x. So x is in R3, x1, x2, x3, n tilde is n1, n2, n3. So these are the 3 Fourier indices, and n4 is the time index, and omega here is the a priori unknown frequency of the periodic orbit. This is going to be, as I said, an unknown frequency or the period, depending on how you like it. So what we do is that we plug that space-time Fourier expansion in the equations of the vorticity equation, and that yields this zero finding problem. So this Fn of W now by definition is going to be I omega n4 omega n. So that's, if you think of plugging the vorticity in that term here, then you'll have a derivative with respect to time. So you have I n4 omega appearing, omega n, plus, and now if you apply the Laplacian to W, then you'll have this plus n nu n tilde square, where n tilde square is by definition n1 square plus n2 square plus n3 square. So that's the representation in Fourier of the Laplacian, minus Fn W omega. Fn omega is the nth Fourier coefficient of the curl of the forcing term, plus some nonlinear terms. So these are the Fourier coefficients of the resulting Fourier expansion after you plug W, or omega, sorry, in the vorticity equation. Okay, so now you have an infinite dimensional zero finding problem. You have infinitely many unknowns. W here is really containing the frequency and all the Fourier coefficients of omega. And when you think about it, that's a lot of unknowns, because now n is indexed over Z4. So you have 4 dimension, again, 3 spatial and one time variable. So that's a very high dimension. I mean, it's infinite dimensional, but there's a lot of it's a lot of infinites, right? So it's Z4. Okay, and now here's a lemma that justifies our approach. Okay, so if W, so let W to be such that the vorticity omega is analytic. Okay, so basically W is the set of unknowns, and once you have this set of unknowns, you can define a vorticity like this, and now we're assuming it's analytic. And it will be in our proof, because we will actually do that. We'll prove the existence of solutions of F in a space of fast decaying Fourier coefficients. Okay, so let W such that the vorticity omega is analytic, and assume that F of W is equal to 0. Also assume that the curl, the divergence of omega is equal to 0. And assume that F does not depend on time, and it has space average 0. So what you can do is that you can now define U to be, well, MW. So MW, that's a way to recover the velocity as a function of the vorticity. So U solves omega is equal to the curl of U. Then, I mean, that's something that is really easy to do in Fourier space. Okay, so once you do that, then there exists a pressure function P, which you can really recover a function P which goes from the 3 torus cross R into R, such that UP is a 2 pi over omega periodic solutions of Navier-Stokes. Okay, so that lemma justifies the fact that now we can actually study the zero of F, which is this map. And once we study that, if we can prove the existence of a zero of that map, then we can recover a velocity, and we can recover a pressure from Navier-Stokes, and in fact, we can even construct explicit rigorous error bounds for U and for pressure after that is solved. Okay, so now we have this zero finding problem to solve, and we want to use the contraction mapping theorem for that. But if you think of a periodic solution, a periodic orbit, and if I express the periodic orbit in Fourier, then solutions are not isolated locally. Why? Because if I take a small little shift of the periodic orbit, then in Fourier that will lead to a small little modification of the Fourier coefficients. And basically that means that locally solutions are not unique. So in order to eliminate that non-uniqueness, then we impose what we call a phase condition. Sometimes you could think of this as a Poincaré phase condition. You fix a Poincaré section and you impose that at time t is equal to 0, you are in a hyperplane. It's one way to see that. So we append that phase condition, and now F has one more component. And now it has, hopefully it has locally unique solutions because we eliminated time shift. Okay, so now this is our map, capital script. So before I had the difference between F script and F non-script, but F script now incorporates a phase condition to this problem. Okay, so a phase condition being incorporated, now we have a map for which we want to study the zeros of the map. Okay, so now I'm in the context of my general, now I'm in the context of this general problem. Okay, so now I have a map, F, to solve, and X in that case is the W, contains the frequency and all the Fourier coefficients of the vorticity. Now I want to solve this problem in a Banach space. So now I better choose my Banach space. So now I'm going to choose it, Banach space. So it's going to be the following. So first, W has 3 components because it corresponds to the Fourier coefficients of the 3 components of the vorticity. Okay, so for each component of the vorticity, I'm going to think of coefficients, of the Fourier coefficients, as living in a Banach space, in a weighted L1 Banach space. Okay, so I fix a number eta greater or equal than 1, and I define the sequence of A defined over Z4, such that the weighted L1 norm, which is the following here. So if eta was equal to 1, then that would just be L1. So the sequences index over Z4 such that that norm here is finite. Okay, so that norm incorporates this weight here. Okay, so it's basically a weighted L1 space. So if you think of if eta was equal, say, to 2, and that would mean that the Fourier coefficients, they decrease geometrically as basically a constant divided by 2 to each of the Fourier coefficients in each Fourier direction. So in the first Fourier direction N1, it decreases like a constant divided by 2 to the k, and then the same thing in the second direction and so on. So in all directions, the sequence decays like geometrically. Okay, so that's for each component, and then the whole Banach space, because now I have W, and again W is incorporating the omega and all of these the 3 components of the vorticity. So then the Banach space is going to be C for the frequency cross 3 copies of L1, and the norm that we choose for W is the sum of the absolute value of frequency plus the weighted L1 norm of each of the component of the vorticity. So that's our big Banach space. Okay, so now we have a map and we have our Banach space, and we chose that Banach space because it is satisfying the following. It is so that each of the L eta 1 is a Banach algebra under discrete convolution. So what does that mean? That seems a bit daunting as for those of you who have not seen what a Banach algebra is, but a Banach algebra only means that if you have a Banach space, and in that Banach space you have a product, which is not always the case, the product in that case is discrete convolution. So if you have 2 sequences of Fourier coefficients, you can multiply that, so-called discrete convolution, and with that choice of norm, then we know that the norm of the product is less or equal than the product of the norm, where the product here is the discrete convolution. Okay, and that's very useful to design this constant that I talked about, this kappa of R, right? Because we'll need to do some nonlinear analysis, because we'll have nonlinear terms, and we'll need to take operator norms and so on. So the fact that we have a Banach algebra really facilitates the nonlinear analysis. Okay, I'm not going to go too much into details. Of course, references for what we do that, but the reason why we choose this Banach space is because of that. And also because it's weighted L1, then we have nice ways to compute operator norms. Because say if you take a finite dimensional problem, or if you take a matrix and you want to compute the matrix norm, the L1 matrix norm, it's kind of easy. It's basically the max of the L1 norm of each of the so you take, you have a matrix L1 norm. So you take the first column, you take its L1 norm, you take the value, and then the second column, you take its L1 norm, and the third column, and so on, and you take the max out of each of these L1 norm of the columns, and that gives you the matrix norm. Well, in infinite dimension, an idea like that is also is the same, right? So that allows us to be able to explicitly compute operator norms in the context of this Banach space. Okay, so that's also a reason why we choose these Banach spaces. All right, so now I want to propose and present an example. So for this, we need to choose an external forcing term. And choose an external forcing term, which is very standard. So that's the so-called Taylor-Green time independent forcing term. So now F does not depend on time, it depends on space. And the reason why this is a nice forcing term is that there is a known steady state for that. There's a closed form steady state. So in fact, it's not so hard to verify that for that forcing term, if you plug the steady state, which is the following 1 divided by 2 times the kinematic viscosity times F star, and P star, which is 1 divided by 4 nu square cosine 2x1 plus cosine 2x2. If you plug that in Navier-Stokes, you'll see that this is a steady state. And in fact, this is corresponding to the so-called viscous equilibrium, the one that Seren proved to exist in the large viscosity, where he proved that for large viscosity, that equilibrium is globally attracting, globally stable. So it attracts all solutions. Okay, so this is in the limit of large viscosity. So when the viscosity decreases, then in that case, there are things that are happening. And in fact, this is how we're going to compute numerically our periodic solutions. So now we have this problem, and now we want to apply this general philosophy for this. Now we have a forcing term, we have the curl to this forcing term, which is again this term here. So now we consider that, we build the zero fading problem that we want to solve, and we apply the general strategy that I introduced in the general context before. Okay, so the first part is to compute a finite dimensional reduction. So what we do, I will not write down all the details, but what we do is that we have infinitely many unknowns. So we take a finite dimensional approximation, a Galerkin approximation. We take only finitely many Fourier modes. So say we have 3 spatial directions and 1 time direction. So we take finite number of modes in the first dimension, the second one, the third one, and the fourth one. And then that leads to a large finite dimensional problem. We keep only finitely many variables and finitely many unknowns, the same one, so that we have a square problem for which we can apply Newton's method. And then that second part, I will give details. And after that, we have to build these bounds. To show that we do have a contraction. So what I will do now is that I will show you how to compute a linear operator A. Okay, so what we have is we want to compute or to construct a Newton-like operator. And when you look at the map that we have, so we have this map is basically that we want to solve has the following. So it has linear parts and it has nonlinear parts, right? So when you take the derivative of this map at a numerical solution, it will have some sort of a form like that. And why a form like that? Because the first row here is the derivative of the phase condition. And the phase condition will have, well, if you derive the phase condition with respect to all Fourier modes, they will all have a row of terms here. And the first column here is the derivative with respect to with respect to omega, right? So you'll have I and 4, sorry, with respect to capital omega, the frequency. And that's only going to lead to I and 4 omega n, okay? And then all the other terms are basically the derivative of Fn with respect to the Fourier coefficient. So that's going to be a linear part plus the derivative of the nonlinear terms with respect to Fourier coefficients of the vorticity. In that case, what will happen is that will lead to just a large, very large matrix, I mean an operator, but which will have a specific structure. And here's the specific structure. So basically the finite block can think of the finite block as the finite dimensional map, for which I take the Jacobian matrix applied at the finite dimensional approximation, and can think also as the diagonal term here as being just I omega n4 plus nu n tilde square, right? So the true Fréchet derivative of the map F applied to omega bar, the numerical approximation, really contains this structure here. And the fact is that because we have regularity in the solution, so I mentioned at the beginning that we do have smoothness in these compact invariant sets. And the fact that we have smoothness comes from the fact that, say, a periodic motion exists for all time. So the Laplacian is applied to it, so that basically it's extremely smooth. And because of that, smoothness implies decay rate in the Fourier coefficients. And that means that when you move away from the diagonal, the terms will actually go to zero because of the decay. You could see that from the convolution. If you take, if you have a nonlinear map, and then some discrete convolutions in that nonlinear map, and Fourier coefficients decay very fast, you take the derivative, then as you move away from the diagonal, you'll actually have these terms, they go to zero because of the. So because of that, we can approximate the Fréchet derivative. We can say, well, the Fréchet derivative here is approximately equal to the finite part and the tail, and I just neglect the rest, okay? That's an approximation. And now what I can do is that I can say, well, this is a very large matrix in my computer, but I can use my computer, put that in there, numerically invert it, and then keep an as an approximation of the inverse, put that in the finite part of my operator, invert the tail or the diagonal part of the tail by hand. Okay, this is by hand, and this is my A now. So A is basically a finite dimensional numerical inverse of the Fréchet derivative finite dimensional problem, and in the tail I do it by hand. Okay, so that really is a computer-assisted operator A that I built. So it's a very large matrix, and the tail is given by the exact inverse of that. And that exact inverse for large enough n4 and n tilde, that's going to be invertible. Okay, so that's the operator A that I use. And once I have the operator A, then I go back to this strategy. Now I have my A. Verify that A is injective. In fact, that will be a byproduct of verifying that I have a contraction. But anyway, and I define this Newton-like operator, and then I build these bounds. And then these bounds, well, I'm just going to show which tools from the two towers I've been using, right? So now that we have the A, then we have to compute. And we have the A, we have the W bar. Now we have to compute the epsilon. So to compute the epsilon, we'll actually use interval arithmetic, which is a way to make sure that you control all floating points errors. Okay. And then we need to compute the operator norm. So then we have this large finite dimensional matrix and the tail A. So A has a finite dimensional part and it has a tail. So that computation here will actually, in fact, be a finite dimensional computation because W bar has only finitely many non-zero terms. So because F has quadratic terms because it's coming from Navier-Stokes, then that computation will actually be a finite computation. Okay, so we have a chosen norm, which I showed before. We use interval arithmetic, and we compute that epsilon term. And then to compute the kappa of R, then we use the tools from nonlinear analysis, functional analysis, because we need to build this operator norm. We use Banach algebras. And then, yeah, the fact that we have a unique solution comes from a fixed point problem. We use Fourier series. So these are the tools from the left tower and from the right tower where, well, we did, I'm going to show you a little bit how we computed that, but we did continuation by say a predictor corrector algorithm. And to compute the nonlinear terms, then we also have to use the fast Fourier transform because we have these convolutions in high dimensions. So combine the fast Fourier transform with interval arithmetic, and we build these bounds rigorous way. So at the end of the day, that polynomial inequality is verified rigorously, and then we know for sure that there exists a unique fixed point of T in the ball, and therefore unique zero of F. And then by the lemma, then once we have that unique zero of F, then we can construct this U and the pressure with rigorous error bounds, and then we can actually get the existence of a spontaneous periodic motion in Stokes. So let me just say that the interval arithmetic that we've been doing was done in IntLab, which is the MATLAB toolbox for reliable computing, developed by Siegfried Rump, University in Germany. Okay, So I have basically, I'm out of time. So basically what I can just say is that what you see here is the Reynolds number is in that case the square root of 8 pi divided by the kinematic viscosity. So when we increase the Reynolds number, we decrease the kinematic viscosity. And what you see on the horizontal axis is the viscous equilibrium. So at some point there is a half bifurcation, and we have proven the existence of two periodic motions, P1 and P2, pretty far from the bifurcation. And I'm going to show you a movie of that. So that's the movie of this second periodic motion. So this is a computer-assisted proof. So in that case, the kinematic viscosity is 0.265. U P bar, U bar, P bar are the numerical approximations. We computed them with 21 Fourier modes in space and 16 in time. So in that case, that periodic motion is kind of still two-dimensional because the forcing terms, from the viscous equilibrium, there's a bifurcation, there's a half bifurcation, and that leads to a two-dimensional periodic motion. So it doesn't really have anything interesting in the third one. Well, the next step is actually to prove the existence of this three-dimensional one. But what you see here is the motion, of the periodic, and that's a computer-assisted proof. So this is a solution which exists for all time, and it has been proven using machinery that I just proposed. And the next step and the final step is to prove this one. Well, not final, but the next step is actually to move to a fully three-dimensional orbit, which you can see here. So that's what we have as another project, the next project now. But all the estimates are fully general. And okay, the goal is now to prove this one, and now it's a matter of computational power. So we are trying to reduce the computational time in our proofs. But one thing I can say is that now that if we can prove this one, then after that, the goal is to move to higher Reynolds number to prove the existence of more complicated periodic orbits and try to prove existence of connecting orbits between periodic orbits in order to show the existence of chaotic dynamics in the Navier-Stokes equation using Smale-Stangel's theorem. So it is known for a long time that if you prove the existence of heteroclinic orbits between periodic motions, then that can lead to Smale horseshoe, and in fact that can lead to proof of existence of chaos. So that would be our ultimate goal, is to move towards high Reynolds numbers in Navier-Stokes, prove existence of several interesting periodic orbits, prove existence of connecting orbits between them using some similar idea that I proposed today, and therefore have some proof of existence of turbulence or, say, chaos in the Navier-Stokes equation. And on that note, I guess I will skip the rest, and then I'll just say thank you.
Thank you very much, Professor Jean-Philippe Lessard. So thank you for your very insightful talk. So any questions, comments, remarks from the audiences, please just unmute your microphone and ask. Yes? Perhaps let me begin, okay? I have a question about your lemma. So you have proved the 2 pi over omega PI solution, right, by contraction mapping principle. And I know if the solution exists, it's non-trivial. How do you guarantee that the period omega is non-zero?
Yeah, because we have an explicit, say that our radius in that case was 10 to the minus 6, and our numerically computed omega was, what was it in that case? As a byproduct of the computer-assisted proof, we have really good control on the location of the omega, right? And therefore of the period. So in that case, omega minus omega bar is, let's recall, an R. And in that case, well, I didn't put it there. But let's say we have an explicit control, right? So if omega bar, say, is 2, then the true frequency is 10 to the minus 6 away from 2. So for sure, the period is non-trivial.
I see. And does your approach say something about the local stability of your PI solution, or just distance?
It does not, in the sense that we could get it. There are techniques to actually do it. Yes, to actually compute the Floquet exponents of the periodic motions. We know how to do that for some finite number of coefficients, and for the because they are, in that case, there are infinitely many Floquet exponents, Floquet multipliers. So there are techniques, we didn't do it here, but there are techniques to do that, to actually compute all the Floquet exponents and show that the orbit is stable or unstable. But in that case, it is believed that this one is stable because globally, the viscous equilibrium, that's Severin proof basically, this one is globally attracting. And when you increase, there's a half bifurcation, that equilibrium loses stability to this family of periodic motions. So it is believed that this orbit is stable. We did not prove it, but it is believed that it is. But in order for that to be approved, to actually really prove that this is the case, we would have to show and to control all Floquet multipliers, which is something we know how to do, but we have not done it for this example.
Thank you. So other questions, comments, remarks?
Perhaps I will ask something. So first of all, thank you very much for the very nice talk. My question would be, well, I understand that you are essentially reformulating your dynamical object as a fixed point of a certain column.
Yeah.
My question would be if there is any especially pathological equation when it comes to obtaining these kind of results. So it seems it works for Navier-Stokes, it works for many other problems that you posed at the beginning. My question is, maybe are like wave equations very bad for this, or is there any very bad equation?
Yeah, there are bad equations, definitely. So what did we do here? We use some structure of the equation to design, say, an approximate inverse, right? And when you go back to this problem here, what we have is that this problem leads to a derivative which has a diagonal dominant structure, okay? So when you think of the Fréchet derivative of this nonlinear map here, then you really have that in the tail, these terms are really growing faster and faster, okay? So, and they are going to infinity very fast. So that's typical for these dissipative type of problems. Now, if I had a wave equation, then I could have, if I was plugging a Fourier series in space and in time, then I could have problems with this structure. Okay, so this structure here, because I could have that these eigenvalues of the linear part, they could be arbitrarily small in the high modes, right? So I could have what we call small divisors. So for this problem, that could definitely be hard to apply, right? So if you have wave equations and then you plug Fourier series, that you could have that these eigenvalues they are not growing nicely, and then therefore you cannot use this structure to get that the matrix here is asymptotically diagonal dominant. If you think of the Fréchet derivative here, that really is it has a structure that it is asymptotically diagonal dominant, which is not the case for many other problems.
Thank you very much. I see.
Thank you, Alejandro. So more questions, comments, remarks? I have another question about the finite dimensional reduction. So because now in your Navier-Stokes, the domain is a torus, so you have this Fourier modes in the space. But in general, I don't have that property, but still I want to find precise solution. So what kind of finite dimensional reduction do you recommend?
Yeah, so well, I mean, I told you before that I was in a conference in Japan some weeks ago, and then in fact there was a talk by Michael Plum and his PhD students. So they are at KIT in Germany, Karlsruhe of technology, and then they have
KIT.
Yeah, you're better than me. Of course, you weren't in Germany. Yeah. So they have his group and also people from Japan, the group of Nakao in Japan. Then they have techniques based on finite elements. So when you don't have a nice cubical domain, then you can still do these kind of things, but now with finite elements. Now the finite dimensional reduction would be to use finite elements, and then you have to change the approach in the sense that now you do not have Fourier representation, but you can still take a finite dimensional projection, do some computations, and there's still a way to actually design a Newton-like operator. But now instead of having this nice diagonal dominant operator, then what you do is that you bound the norm of the inverse using eigenvalues enclosure. So basically you have a Fréchet derivative, you have a finite element approximation, and now you use different tools from, I mean, it is completely a different set of tools, but you use this rigorous location of eigenvalues to compute the norm of the inverse, and you can still apply a contraction mapping to prove the existence of solutions to Navier-Stokes using finite elements.
Thank you very much. And other questions? Yes. Okay, it seems that this is not the case. So let's thank the speaker, Professor Jean-Philippe Lessard again.
Thank you. Thank you very much.
Thank you.